All right, so summation notation helps us to write what we're looking for a lot more efficiently. It means that instead of having to write 1 plus 2 plus 3 plus, we can say the sum from 1 to n of whatever we're adding to each other. So especially when it gets quite long, this is a much more efficient way to write things. It takes a bit of getting used to, but it's not too difficult to use. All right, so this one says, use mathematical induction to prove that the sum from 1 to n of 2r minus 1 is equal to n squared for all positive integer values of n. So what we're required to prove is that our sum from r equals 1 to n of 2r minus 1 is equal to n squared for all positive integer values of n, and that then means that n is greater than or equal to 1. Now we follow exactly the same method for our proof as we did before. So the first thing we're going to do is verify for n equals 1, and we're going to have a look at our left-hand side. So our left-hand side says, now we're going to put n equals 1. So we've got the sum from r equals 1 to 1 of 2r minus 1, and that's just going to be 2 minus 1, which is 1. And our right-hand side, well, our right-hand side said n squared, and that's 1 squared, which is 1. So therefore, my statement is true for n equals 1. The next step says, assume that my statement is true for n equals k. So that means what I'm looking for is that my sum from r equals 1 to k of 2r minus 1 must equal k squared, and that will be for all positive integer values of k, and k is greater than or equal to 1. And I'm going to run out of space. I've been too big here. Let me just shrink this a little bit. Oops. Okay. So the next step is that I need to required to prove that my statement is true for n equals k plus 1. So in other words, I'm looking for my sum from r equals 1 to k plus 1 of 2r minus 1. And we want to show that that is equal to k plus 1 squared for all positive integer values of k, and k is greater than or equal to 1. All right, let's have a look at our left-hand side. So our left-hand side says our sum from r equals 1 to k plus 1 of 2r minus 1. Now, I know that that is the same as saying my sum from r equals 1 to k of 2r minus 1 plus, well, my next term after k is just going to be 2 times k plus 1 minus 1. Okay, so this is my up to k, my inductive hypothesis. And this is my next term, or my k plus 1 term. Okay, now I'm writing it like that because in my inductive hypothesis, if I go back to my inductive hypothesis, this thing over here is actually equal to k squared. So I can then quite easily say that is equal to k squared plus 2 minus 1, which is k squared plus 2k plus 1. Okay, and I see that's a perfect square, and that can be written as k plus 1 squared. I forgot to write here using, you need to write this please, the inductive hypothesis, and that's equal to my right hand side. Okay, so therefore my statement is true for n equals k plus 1, and then I just need to finish off saying that my statement is true for n equals 1, 2, 3, all the way to k and k plus 1. Therefore, by mathematical induction, my statement is true for all positive integers n greater than or equal to 1.